It's usually you and Peter here.
Yeah. Wait, but so there's usually only 3 people there and you sat here?
No, me and Peter sat there.
Me and Peter.
Oh,
So in this chapter, what I want to look at, this is only going to be like 1 or 2 class periods worth of time. It's not a lot, but there are some cool videos I want to show you, some different tests that you can run to do this. So some of the machinery for these kinds of tests for material science are huge. So it's stuff that you would only have in like an actual engineering lab at university. So we're gonna talk about something called like a tensile test, a compression test, and then there's other tests that are called like surface quality tests. If you liked chemistry at all, if you found chemistry interesting, this is definitely kind of in that area. Material science is a specific type of engineering that a lot of engineers specifically work in nowadays. Why do you think nowadays more than in the past? Why would you think nowadays there are more, or it's a more prominent field, material science? What do you think?
I mean, as we develop different materials, they certainly get lighter, also get stronger.
Yeah, there's been a big push.
Material or eco-friendly material or...
Those are all great examples. Eco-friendly first, environmental stuff for different materials that are now made. Things that are structurally sound, yet very lightweight or low cost or little material. And now, obviously, with things like 3D printing things, that's been a huge push because now you can get certain materials into shapes and structures that you never could in the past. Or you couldn't with ease, at least, right? You couldn't do this with ease. So material science right now is a big field. It's also big because a lot of material science has to do with chemical engineering, which is big because of pharmaceuticals. We know that like there's always that push for a new drug, a new medicine, a new this or that to either help or hurt mankind, depending on the interest of the person that's looking to get paid, right? So we're going to see that there's going to be a lot of applications of this to things nowadays. When I studied materials engineering in college, what we primarily looked at was failure modes. So we looked at compression and we looked at tension. And we looked at other phenomena that we're going to talk about. For example, buckling. What is buckling? How does it actually work? And then this will kind of lead us into the concept and the idea of structures that we're going to look at. So we looked at moments and forces, and I had you guys do the boom lever just to kind of like try things without learning about structures, without learning about trusses. After this, we're going to carry it into the idea of structures, and then specifically how certain structures are supported with different types of supports, really. I mean, or members, I guess you could say. Different orientations. Let's see. Another part of material science that's important is figuring out when you're designing something what you're going to make it out of. You guys had a very limited choice for the boom levers. It was balsa wood, basswood, and then dowel rods. That was pretty much the 3 things you could have used. At the top, you had like, you could use scrap wood, so there was like plywood over there. But for the most part, your material was clearly wood. What was the one choice you kind of had, though, that groups varied with? Glue. Okay, glue was your material that you could kind of like choose what you wanted to work with. And if you notice, Johnny, right, didn't your groups, is that where it failed actually, at the glue? At the top, didn't it pull out of that spot? Yeah. So some of the members or some of these different structures were structurally sound. Same with yours, Ryan. Yeah, because yours was actually, it was up at that at a mitered angle at the top, and theirs was a dowel rod that pulled out. So the idea, though, of the materials as a choice is a big deal. And you can clearly see that, and although that's a very small example of it, we could see that that does affect our design. Let me lock the screen. There we go. All right. So this first slide. Depending upon the application itself, obviously different materials are going to be useful. So if you were, let's say, what's something you guys would be interested in? If you're a baseball bat manufacturer, what are some things that might be important when selecting the right type of wood and then actually working on that wood to get the actual shape? Durability. So what affects durability? What are some of the parameters, maybe? Some of the material properties? Yeah, the yield strength of that actual wood. And for a baseball bat, what are you really concerned with? You're more concerned with something like tension and compression, because when you hit the ball, what is the bat doing? The bat is acting can lend a boom lever. I know this is hard to believe, but it's cantilever. A baseball bat hitting a baseball is an applied force at a given location. That's exactly what you guys did. When that boom lever was hanging over the edge, there was an applied force pulling down at an exact location. This end was fixed. Well, that end that you're holding in your hand is fixed. So that, fluctual rigidity or that strength in bending is what you have to worry about when it comes to a baseball bat. Now, because it's made of wood, what do you know about wood? Anyone that knows anything about their properties of materials? What do you know about wood if you think about it? There's something specific about wood. Like for example, wood exhibits certain properties of its strength that steel does not. What's the difference between steel? I mean, there's a lot of differences, obviously. But what is a clear difference between steel and wood? If you think about this, it actually makes a lot of sense. If you think about wood, it's not that hard to break wood for certain reasons. Anyone that's done karate before would know this? Yeah.
Depends on the grain.
Yeah.
If you go with the grain, it's easier to break.
The grain of the wood absolutely affects the strength of the actual material. So when loggers actually cut down trees and they want to do things like manufacturing 2x4s, they actually put them through at a certain angle. They have to make sure that the grain of the wood is a certain way. And when you go to Home Depot, you're selecting wood. You always avoid things where you have these big knots in the wood, because that's a stress concentration area. That's where that piece of wood will fail first if it's under an equally distributed stress at the actual knot. So there are certain materials that you have to consider. So it's based on the application. If you're, if you're putting shelving up at home, right? You might get a bracket that's made out of some light-duty metal, because it really doesn't need much to hold a simple shelf on the wall, especially if you're putting picture frames on it. But if you're putting a 50-inch TV on the wall, you need to make sure that the actual bracket itself is structurally sound. That's not going to bend. So based on the application, you might just use simple wood with really cheap metal for the brackets for a shelf. But for a TV, you want to have that bracket that comes off with a certain material. And usually that material has a lot of strength. So it might be something that's a little bit more heavy duty, a little bit more expensive, but because of the application, you choose a different material. There are many other examples of this. And obviously you guys can probably think of a million. If you've ever seen any of those shows, how it's made, how stuff works, those kind of engineering shows either on History Channel or Science Channel, whatever channel we're on, Discovery Channel a lot of the time, a lot of these things have to do with applications. So depending on what you're actually designing and building, your material selection will vary. Okay, so it's application-based. These are some of the considerations we talked about a moment ago, but more over the four main ones that we were considering. Okay, the material properties themselves. So, some of the properties we're going to look at, we're going to look at in this section, we haven't looked at it yet. Things like density, modulus of rigidity, modulus of elasticity, how much it can stretch by, how much it can be torqued by. Density, we said, what are the material properties? Heating, melting point. Other material properties. Coefficient of friction of that surface, that one individual surface. There's lots of properties. It doesn't, anything you think about a material is a material property, and there are many that you have to choose from based on the application. We talked about cost. So if you're, again, putting up a simple shelf in your room, you get a cheap bracket. I put brackets on the mound that we built in the gym that's there for pitchers, and the brackets that I got were the heavy-duty ones because of the fact that it was worth spending double the price because we wanted to make sure that those legs didn't snap off, and that's why we're buying the brackets. Buying something brittle and cheap might not have worked very well, it might have actually broken off. That little cross member there might snap. So it depends on the application again, how much cost you want to actually apply to this. Obviously, if you're thinking about engineering on a big scale, your goal is going to be always to minimize cost. The lifespan. Think about an example of lifespan of material choice. Give me an example of material or a scenario where you may choose one material over another because of the lifespan of that project. What kind of a project could we be considering? Think about big engineering projects.
It's a bridge or building has to stand for a long time.
Absolutely. That's a great example, a bridge. Okay? And I think last year, I think I'll do it again this year, I showed a video on the Brooklyn Bridge. And part of the decisions that are made are about how long is this bridge planning on being there for? Are we going to renovate this bridge every 10 years? Are we going to replace it completely 15 years from now? It really depends on the lifespan that you're looking for. And then the fourth part, think about method of repair. So compare the two things, ready? Electrical cables outside your house, underwater cables that carry transcontinental signals between Europe and the North American continent. Which of these two clearly has a harder method of repair? Obviously the one under the water. So in that circumstance, in that case, you need to make sure that you invest, you plan for a high cost because of the fact that you don't want to be repairing this a lot. You want the lifespan for something like this to be a very, very long time. You want the method of repair to be very easy. So your material that you choose is impacted by these parameters. Okay, by these parameters. There are three major categories that we look at. And obviously there are subcategories of these. We're going to look at electrical, mechanical, and thermal. Electrical, mechanical, and thermal. Anything to do with computers, anything to do with electricity goes into electrical, obviously. It could have to do with the conductivity of the material, if it's good at conducting electricity. It could do with the temperature that it can actually gain before it starts to maybe melt. You could relate electrical and thermal in that sense as well. Mechanical, obviously, we're talking about things like, viscosity of the material. So if you want water to flow through a pipe, why is PVC a good choice, right? Why do we use PVC? Besides, obviously, lower cost than using like copper pipes everywhere, PVC also has a characteristic of it that allows for flow to carry easily through it. It has to do with the actual surface of the actual PVC. When you look at water flowing through a pipe, it has what's called the viscosity profile. Along the pipe, the flow is much slower. In the middle of the pipe, the flow is fastest. For PVC, that profile is not as extreme. It doesn't cause that slowdown of that flow as much as other materials do. It's a good choice for that. That's a mechanical example. Yeah, but these are the three categories that we're going to specifically look at. So, the material properties of something depend on several things. They depend on several things. So first, we're thinking about processing. And by processing, this means how was it actually created and made? So for example, if you study material science, you'll learn that the rate at which you cool down a substance from liquid to solid affects its structural integrity. And you've seen this before. How many of you watch Game of Thrones or any of those kinds of medieval kind of things? Or read a book like that before? No, really? No one's into that at all? I do. Well, if you make swords back in the days where we had knights and stuff, when they made swords, the rate at which they cooled the metal affected the strength of the sword. It's called quenching, I think is the term. It has to do with heating it up really to extreme temperatures and then cooling it very quickly. It affects the actual microstructure of the material. It's pretty interesting to think about that. The actual process by which this product is designed and made affects its parameters. If you're 3D printing things, the speed of the actual nozzle that's moving, the rate at which it's flowing out, the thickness of the layers affects the strength of the actual thing. So I'm printing these things for admissions. I could care less if they were able to withstand 20 pounds of force pushing down on them. They're trinkets. They're made to look nice. That's it. So I'm printing these at quick speed, high speed. I don't care about layer thickness. But if you're printing something that you might be using, I don't know, to hang up part of a shelving, the blinds, the units at the top, or replacing a little plastic piece, you might want something that is much more structurally sound. So the way in which it's processed, the size of those little honeycomb structures inside of the 3D print affects its actual structural strength. The thickness of the layers on the outside, the walls, the amount of layers of walls affects it. So how the actual material is processed. And this really goes into a lot of chemical engineering with processing. The age of the material. Give me an example of age and how it affects the material. Age. Wood. It's a great example. If you have wood that's not pressure treated, that's not made to sit outside, it's been outside for even a couple weeks, what's going to happen to the wood right away? It rots, and what else? Mold, rot, but something structurally about the shape of it. Yeah, it warps completely. The humidity causes wood to warp that's not made for this. So if you're ever building a deck, you never get regular just 2x4 lumber. You don't. Or else your deck is going to start to look like this after a couple weeks. You get pressure treated wood. You get wood that's made to withstand this. I mean, think about it. How many of you, I know a few of you have houses where there's like water a lot, right? Well, those pillars are actually wood. They're just made to be in the water all the time. So certain material, based on its age and based on its environmental wear and tear, can be affected. Its structural strength, its integrity, its material properties themselves can actually vary over time. So the actual age of it. The chemical makeup, obviously, it's what it's made up of. Okay, if we're looking at something like steel versus aluminum, aluminum is very, very lightweight. But aluminum is not very strong. Steel is heavier, much, but steel strength is exceeding aluminum by, thousands, by factors of thousands. That's why aluminum foil is made into foil sheets, so you can crumple it. That's the whole reason for it. Think about aluminum foil. If aluminum was actually a really strong material, even the thickness that it is, if it was really strong, it'd be tough to actually do that. But aluminum is actually very weak in its structural strength. The chemical makeup. Defects we talked about. One of the examples I gave was like where you have a knot in the wood or the actual grain of the wood itself. And usually what you do as an engineer to account for this is you apply like an inverse factor of safety. Remember the concept? What was a factor of safety? What was a factor of safety?
Like when the elevator has a weight capacity, but they say it's a number greater than what it should be to protect you.
Yeah. You give like a little bit of a warning almost and say, yeah, this could hold this much, but don't exceed this much, just so you know. Well, that's the same thing with these defects. These defects have factors that are incorporated into its structural strength. So if the applied load was 20,000 pounds of force at a given location, maybe that's calculated as 30,000 because of the defect. That's a 1.5 factor. Well, 1.5 times 20,000 is 30,000. That's where you get that increased load suddenly because of the defect. The last part that I look at is temperature. Where have you seen this before? Where have you seen the temperature affect the structural integrity of something?
Well, if it's wood, doesn't it stretch if it's really hot? Like it rides out?
Temperature definitely affects wood swelling. It's also humidity for that. A lot of humidity really, but temperature causes humidity. What else?
Bridges grow in the summer and strengthen.
Exactly. When you go over a bridge, you ever see the teeth on the bridge? Bridges are made to contract and expand. We've talked about this, even in physics we talked about this. Roadways, potholes. Potholes in the road come from the concrete expanding and contracting in the different seasons. So because we live in a world where there are seasons, we have to think of cyclical loading. Cyclical, meaning that in certain times of the year you have high temperature, and then low temperature, then high temperature, and that affects the roadways, it affects bridges, it affects structures in general. Okay, it affects buildings. Buildings are made to be structurally stable, but they're not made to be completely static. Buildings are not made to be completely static because of the fact that we have earthquakes. If buildings were not able to move and any sort of shaking would cause them to start breaking, we'd be screwed. There's earthquakes all the time. We don't feel them. We really don't. They're low enough on the Richter scale that they're not even detected or they're not even publicized. But there are earthquakes a lot more than you'd think. And structures can actually absorb that shock. Forget, we talked about in the beginning of the year, right? The New World Trade Center we talked about, the whole concept of it. But the idea of your geography playing a huge role. Well, temperature is affected by the geography also. So there are a lot of things that come into play when choosing materials. And you can, you can study you can do your whole major on material science. This in itself not only is one course, this is like an entire branch of engineering. Material science and materials engineering. Again, if you like chemistry and that interested you, this could be an interesting area to study. Not too much math. It's not heavy math actually either. So if you're not like in love with math and excited if you want to, maybe have to take calculus in college, you're not planning on it, you don't want to, this kind of field is actually a really good field if you like chemistry too. Alright, so let's look at some examples. Okay, just to run through some examples of ones that we've either talked about in physics already or things that they might be new to introduce to you. We've talked about electrical resistivity. Okay, we've talked about resistivity. Where did that come into play? Where did that come into play? Remember Ohm's law of V equals IR? What do those things stand for? What did V stand for? Think back. What is it? Voltage. Voltage. There are three V's. There's volume, velocity, and voltage. So it was one of those three. What did I stand for? Current. And R? Resistance. Good. Okay, current, voltage, resistance. Electrical resistivity is exactly that. It's the resistance of a material. So we're talking about, for example, when certain wires are maybe gold-plated, or certain electrical applications, certain fiber optic cables run faster than others. The resistivity, the rate at which it transfers your electrical signal. Density you all should know by now. Okay, now density, remember, who's in stats? Raise your hand real quick. A couple of you guys, right? The three of you? All right. In stats, you guys study density a lot, but not mass density. You study things like population density, or maybe any sort of concentration of a given parameter in a given space, whether that's an area or a volume, depending on what it is. But you look at data that involves density all the time. You just don't realize that. When you see population maps when you're a kid, and you see like all those dots on the map of where there's high population, you see New York is like flooded with it, India, China, you see all those dots everywhere on the map indicating a lot of population. That's a population density map. Okay, it's the same thing as if like you were remember in biology, you studied osmosis. Well, that's the same idea. Osmosis had to do with the concentration of whatever was inside the cell versus outside the cell. If there was a difference in that concentration, it caused a differential, which caused flow from one to the other through the cell membrane. Well, that's concentration, that's density. So there are many versions of density. Specifically in engineering, you look at the density as in the mass over the volume. Density is a huge factor when it comes to anything to do with fluid mechanics. Anything with fluid flowing. With air conditioners, with pipes in the wall, with fluid coming out of the faucet in your house. All of that is affected by density. Okay, by density. You guys are not of age, but I'll talk about this because it's really interesting and I think you'll like it. If you decide one day to brew your own beer, density and fluid mechanics and properties of it has a huge impact on the taste of a beer or wine or anything like that. It really does. And it's true, the actual density, you call it the specific gravity of it, affects the amount of alcohol content in certain things. So if later in life you want to appreciate alcohol and you decide to either have your own distillery at home, or you do your own thing with wine, or you want to have a home brewing thing. So much chemistry involved in it, it's incredible. There's a lot of chemistry. I haven't personally really dabbled in the area as much as I'd like to, but I lived with two guys who were actual brewers that ran breweries in DC for a long time. They ran breweries that had 40 microbrews on tap at a time, and they were in charge of the whole thing. So I learned everything from them about it, but I didn't actually ever do it myself, and I haven't invested time in it. It's difficult. It takes a lot of time. It's more of a summer project I've been looking to do. Something that's just interesting to do. But again, a lot of chemistry involved. The density affects so much about the actual beer itself. And I think for things like wine and liquor, it would also do that. Again, when you're of age, you want to try these things. All right, the next part, the modulus of elasticity and rigidity. So the modulus of elasticity is also known as what's called the Young's modulus. Scientist's last name, they usually name it after the person. The modulus is like the equivalent of the K value. Anybody remember from physics last year with springs? What did the K value represent for a spring? What was the K value? Yeah, the strength of the spring, the rigidity of the spring constant. So if it was a lot larger K value, it took a lot more force to stretch the spring. E, this is capital E, the modulus of let me put these variables down, by the way. This is capital E. Density is rho. Is resistivity? Resistivity could be either K or R. It really depends. If you're looking at the resistance, R is used. If you're looking sometimes at resistivity, you could see K. The elasticity is really a measurement of the strength of that material before it starts to either, buckle, compress, stretch, before it starts to permanently deform. Have you ever taken a rubber band and stretched it too much? What happens in the very middle? What do you see happen physically? Yeah, it starts to get really frayed and thin. It starts to vibrate for a little bit. You'll see the very middle of it start to get really narrow. It's called necking. It's a property, it's a phenomenon called necking, where you pull on something enough, and what happens in the middle of it is the material starts to permanently deform. How about a plastic bag? Take a plastic bag and stretch it enough. What happens? It gets permanently deformed in the shape you pulled it to. It doesn't go back like a spring would. A spring goes back to its shape. A plastic bag is plastic. Plastic deformation is when something stretches beyond its capacity to go back to its original shape. So Young's modulus, the modulus of elasticity, is what affects an object's strength in tensile or in tension against the tensile force. Modulus of rigidity. Write down, this is the shear modulus. Write this down. This is really shear modulus. What was shearing, if you remember? We talked about this. We did an online kind of thing, talking about shear force, talking about bending, compression. What was shearing?
Is that when a bolt compresses and they go in opposite directions, the two forces, so they overlap each other?
Yeah. So it's either twisting or overlapping. It's one of those two. So this could be, as Alessia said, torsion. It could be twisting, or as Julia mentioned, where, remember I talked about this? There's a bolt, and it's attached to two pieces on a floor. And imagine these two pieces have stress outward like this. One is pulling this way, one is pulling this way. It would cause shear stress in the bolt, and it could snap. That has to do with the modulus of rigidity. The higher the modulus of rigidity, the stronger it is in shear strength or in torsional strength. Okay? In either of those two. So for this one, we'll write shear. Let's jot these terms down because this is where they're utilized. We'll write shear modulus, and then also let's write down torsion. This is used in tension and compression.
That's when everyone's shining. Because it's the theme. It's no limits. It's the future.
Scroll down a little bit. I have the table on the next slide.
I did.
So, obviously, these are self-explanatory, but why is it important? Why is it important that we publish data about tensile strength and compressive strength? Think about it. Young's modulus, or the modulus of elasticity, is already giving you the strength of the material, and that's either in tension or in compression for that material. Why is it important that we talk about these separately? We talked about this already once this year. We alluded to it.
Different materials have different properties when it comes to tension and compression.
Exactly right. We talked about this with concrete already. Concrete is extremely strong in compression. You see concrete pillars all the time, don't you? But have you ever heard of a concrete beam? No. Concrete beams aren't used because concrete beams would have a force applied to them which would cause tension on the top. It would just be brittle. It would break right off. Bridges, yeah, sure, they're concrete, but they're reinforced with rebar, with steel plates to take on the load of the tension. whereas the concrete takes on the load of compression on the bottom. Remember we talked about bending? We talked about bending. And when we think about bending, think about a dowel rod. You're literally bending it. When I bend this, when it breaks, you're going to see that at the top, if you look at this, the top was in tension, it snapped apart. The bottom was in compression the whole time. So when you talk about things like bending, that's what you have to consider. In a minute, we're going to talk about, well, what's the difference between me compressing here, right? If I just compress, I can't really break this. But if I take this, push down like this hard enough and compress, it'll eventually snap if I were to fix this end. If I push down enough, this is called buckling. So we're going to see that in compression and in tension, the properties are different. So you have to know what the actual member of your structure is in. If it's in a state of stress where it's compressed, you might want to use one material versus another, as opposed to another. Let's finish with some, we'll start next class with a couple cool videos of this. I want to show you guys some videos. But just so you have an idea of like familiarity, these are just traditional materials that you use for structures. And you're going to see that you have a shear modulus and then the regular modulus. This modulus is the one that's utilized in tension and compression. The one on the right is the one that's utilized in torsion and in shear stress. In torsion and in shear stress. The next table I want you to see, okay, is the one that we're going to see what's called yield and ultimate strength. Yield strength is when that material will start to fail. Will start to fail. If you continue past the yield strength, you will reach what's called its ultimate strength, and it will actually reach its failure point. So a material fails for some time under stress. It's kind of interesting. You start to apply a certain amount of force to something, it will start to bend and bend and bend, and it will start to yield until, and you saw this with your boom lever. Johnny, was it yours that really bent a lot on the bottom, right? Theirs was yielding for a long time. It started to really bow out. Those are things that you don't want to happen to structures that you'd be walking over. But it yielded for a while until, actually no, it never reached the ultimate strength. It never reached its ultimate strength. It actually, the glue at the top is where it separated. So the bottom that was yielding, that was bending, never reached the strength and it never actually failed. Okay, but we're going to see that we have this, and we have to recognize, look, some of these materials, in parentheses, you're going to see compression, or you're going to see tension, in parentheses 10. Okay, let's go down and look at a few others. Concrete's not listed. I'm surprised there's one of these in this table.
It's right there, compression.
Where is it?
Under past one.
Ah, there it is. Thank you. And it's only listed in compression. Concrete, the value in tension isn't even published because nobody in their right mind would ever use it in tension because it's so weak in tension. All right, we'll stop there for today. Now, you apply more and more and more stress until you get to right here. Then at this location, you don't have to apply a lot more stress at all. You apply only a little bit more stress, and suddenly this thing elongates a lot. And that's what this is right here. Okay, this is that term I called necking the other day that a few of you laughed at, necking right here. Okay, you see this little neck, okay, where the middle starts to kind of like slender. So when that happens, it continues to stretch more and more and more, and more stress is applied until the material can no longer even hold that stress. So the machine lowers in the stress applied until it fractures. Okay, until it fractures at the very end. And that's where that snapping occurs. If you've ever seen this, and I'll show you a video of it, but in person, it's actually kind of cool. You'll watch it, you can watch the specimen, you'll see it start to narrow in the middle more and more. All of a sudden you hear a pop, and it just snaps. And it like just completely fractures apart. So this is an example of a tension test. This is also done for compression. And for compression, you're going to see it starts to narrow, it starts to get shorter and shorter and shorter until it fractures in the middle. It's a little bit different than this. Maybe I can find a compression test to show you that too. So along the stress-strain curve, we're going to identify 5 points. So let's jot these down. Okay. The first thing that we want to look at, I'm going to start with number 5 actually. Okay, number 5 is indicating what's called 2% offset or 0.2% offset strain. And what this means is you can go to about 0.2% strain, which is really, really small. It's not even, if you had a specimen that was 100 centimeters, which is like, think about 100 centimeters, that's a meter second. If you had a specimen that long, 0.2%, that's 0.2 centimeters, it's very small, 2 millimeters of stretch. So under this much stretch, if you take a line parallel to the motion of the stress-strain curve and see where it intersects at 0.2 up there. So follow this along. If you go to 0.2% offset strain, meaning it stretches very little, and run a line parallel to this line that is represented by the stress-strain curve, this right here, notice this is Hooke's law right here. F equals Kx, linear. Remember Hooke's law? Jot down Hooke's law. Hooke's law tells us Fs equals negative Kx. Well, if I graphed it, I would graph it as positive Kx. From the beginning until 0.3, you have the proportional range, or the elastic range. This is called the proportional limit. Proportional limit, or you could say that this is the elastic limit or range. Once you reach that point, the specimen no longer stretches like a spring would. Think about how a spring works. You did this in physics. You apply more force, it stretches more. You apply double the force, it stretches double. You apply triple the force, it stretches triple. Well, once you reach 0.3 on this graph, it no longer stretches proportionally. So if you apply a little more force, it stretches a lot more suddenly. So after number 3, which is the proportional limit or the elastic limit, it's called elastic because within this range, from the beginning to 3, the specimen will return to its original shape, like a spring does. Think about a spring. You pull on a spring, it stretches. When you let go, it returns to its original shape. That's the elastic range still. So up until 0.3, this is really just an example of a spring. And you're going to see at the bottom, we have our stress-strain relationship here at the bottom. I'll put a box around it. That's the same thing as Hooke's law. It's analogous. This stress, this is called sigma. This is the stress. You should probably jot these things down so you know what they are for your quiz on this. This is the stress. The stress is like the amount of force you apply. This signal here, epsilon, this is the strain. Strain is plotted along this axis. It's like how much it stretches by. And E, if you remember from the other day, we talked about capital E, that was called the modulus of elasticity, or Young's modulus. This is how much it will stretch by. This is a material property. It's just like K. K was a property of the spring. This formula for stress-strain curves is analogous in nature to Hooke's law. And this is showing the region from here up until the proportional limit. Now again, once you pass the proportional limit, as you apply a little bit more stress, it changes shape a lot suddenly. And at 2, you reach what we call the yield strength. This point here is when it starts to yield, meaning it starts to really, really, really narrow. And then you'll see what's occurring here. Okay, you're going to see it start to yield and it starts to stretch a lot until you reach this fracture or this necking and then the fracture point. So again, it yields at this point, which means it really starts to stretch more and more under very little increment of change here. Notice I don't go up much for stress, but I go over a lot for strain. I barely go up. I apply very little force or not much more force than I was applying a minute ago, and suddenly I stretched all this far. So this function, instead of being a very, very increasing function, now flattens out. It almost reaches like a limit. In math class, you would learn about limits. This is a limit that it retracts from, though. It doesn't ride along the limit like asymptotic behavior or an asymptote. It's not an asymptote. At this point here, though, number 1, we're looking at what we call the ultimate strength. Let's label number 1. Ultimate strength. The ultimate strength is really the ultimate stress that it can withstand. It's the highest sigma value. Look at the y-axis is sigma. The x-axis is this epsilon over here. This is how much force is applied really. This is by what percent does it stretch. Well, the highest force it applies is the highest sigma. We call it the ultimate strength. That's the maximum on the curve. In your pre-calculus class, you're learning about maxes and mins. If you're in pre-calc, obviously. Okay, where you've learned about maxes or mins on the graph, the highest point and the lowest point. Aren't you graphing trig functions, or didn't you do that already? Hello? In pre-calc, didn't you graph trig functions? So you have peaks and troughs, or maxes and mins? Correct? You've been identifying those as locations? That's what this is here. The ultimate strength is the max point right here. It's that location. Then what happens is it continues to stretch more and more until it reaches point 4. And point 4 we're going to call fracture. So again, point 5 is 0.2% offset strain, showing that it's stretching by a little bit. If you put this line parallel to the actual proportional region, you'll reach a location where it intersects with number 2, which we call the yield strength. We call it the yield strength because this is when it begins to yield. It begins to stretch uncontrollably. It's like when you take a slinky and you pull it on it, and one person pulls on one end, one person pulls on the other. If you pull hard enough, what's going to happen to the slinky? It deforms permanently. That's what this is. Yield strength shows where it starts to permanently deform. Where that curved region is, this curved region, is when it's actually deforming. So the test that you perform really tests for all of these locations. And if you look at the graph, and I'll show you the graph of it along the way, you'll see all of this. So let's pause at this point and take a look at some of these videos. So there's a couple videos, and I want you to see the difference in different materials and how they behave differently. Alright, so we'll start first with this one. Do me a favor, close your iPads while you're watching so I know that you're focused. Because clearly some of you are not paying attention right now. So we're going to take a look, and we're going to see first an example of metal under tension. Johnny, please pay attention. We're going to look at metal under tension first. So we're going to load a specimen, and this is just the name of the metal, ASTM E8. We're going to load the specimen. That specimen is going to then be pulled on in tension. We're going to see that actual range of the stress-strain curve. We're going to see the stress-strain increasing. Then we're going to see that it starts to yield. And when it starts to pull, that's when the yield happens until it gets the max. And then it reaches the end, and it's going to see it pop. You're going to see it snap. I'm going to show you several. I forget if this one shows the actual graph. I'm hoping it does. But look, what did we just talk about, guys? The following properties are calculated from this test. Offset yield, that was the 0.2% offset. That you knew where to draw the parallel line. Ultimate tensile strength, the maximum of the stress-strain curve. Elongation is the strain along the x-axis. So here's the machine right here. So this is the specimen that's loaded here. This is a gauge that's measuring the length of the specimen. As this gauge moves, because the specimen is getting stretched longer, this recording is fed into the computer, which is read out on a graph. These machines alone cost we're talking $20,000, $30,000 for one of them. So you see them in university level engineering labs. So take a look. Here's the rate. It's going to pull at 0.005 inches per inch per minute. Inch per inch has to do with the amount that it changes over the original length. Think about the amount it changes. What would you measure it in? Inches. The original length is in inches. That's why this is inches per inches. So this is really, if you think about percent, it's going to be moving over here. 0.5% is going to stretch every minute. So this is going to be a fast version. What is that called? Time lapse of the actual test. So here's your stress-strain curve. Before we go further, look. As more stress is applied, proportionally, it stretches more. in this region, it follows Hooke's law. It's acting like a spring. If we stopped right now and removed the specimen, it would go back to its shape because it hasn't reached that curved part where it starts to yield and actually start to become what's called plastic deformation, like a plastic bag. That's the term. So, let's see if we can see the member itself as it's happening. So, so you see how it's necking in the middle? Look at the middle. The middle's going to keep getting narrower, and then it snaps. When it snaps, so they're measuring the overall elongation of this. When it snaps, we're looking at what we call, again, the fracture point. So this, take a look. What do we say? This was the 0.2% off yield. So look, if we move this over to be a percentage, it's going to be 0.2%. This means that 0.2% of this has stretched. So again, 0.2% would be like 0.2 centimeters on a meter. So a specimen that's this small would be much less than even 0.2 centimeters. If you draw a line parallel to this region here, this is the location that indicates the yield stress. This is where the actual material enters what we call the plastic range, where it really begins to stretch a lot. That's the mathematical way of locating that location.
Is it only 0.2%?
Yeah, the traditional one is 0.2% off yield. It's just been like the accepted rate. I think that's it for this. I'm just trying to jump ahead if there's anything else. So this is what they end up coming out with. Take a look. Take a look. The maximum stress that it could withstand, the yield stress that it withstands, so right up to here. At this point, it's many pounds per square inch PSI. At this location, that's when it starts to become plastic deformation, and it reaches this much at a max, and then starts to dip back down. They didn't show the dipping back down part. It elongated by 35%. It's pretty incredible to think about that. That stretched an additional third of its original length. So buildings, although maybe like a beam starts to bend, it will deform a lot before it actually fails. Metal is, what's the word for that? When it will bend a lot before it will fail. What's a word for that? What's a mechanical word for something that will stretch or bend? Flexible is good. What else? It's elastic. Good. Think about art class. Clay is very what? Moldable or malleable is the word. Metal is very malleable. Therefore, this is a high value percentage. Let's look at another thing. Let's look at Kevlar. Let's take a look at Kevlar. Take a look, please. Look up. Look up, look up. Look at the stress strain plot. Stretching very lightly, following Hooke's law. It's going to start to curl down. This is the Kevlar specimen itself. I'm pretty sure that this fails abruptly. It doesn't stretch much at all. It is not very malleable. Kevlar is very strong, we know that. I'm pretty sure this one is just going to snap. I don't think it actually ends up netting too much or narrowing too much in the middle. Hold on, it's almost not that happen. I think it just pops in the middle. It's going to happen.
Wait for it.
Actually, there it was. I don't even think you see it. Whoa! Maybe it was, no, that was tension. Let's look at that very ending again. Let's see if we can hear anything. Hold on. It's just rescaling. There's when it broke, right there. Did you see it just like kind of pop? That was anticlimactic. Hold on. I'm going to fast forward a little bit. This is carbon fiber. This is carbon fiber. So still elastic range. Girls. So loud. I want to see if this one's a little bit more interesting ending.
I said it's a unit half.
Okay. So take a look here. We can see this one a little more obviously. So carbon fiber actually, I think it looks like this breaks at the ends. Take a look. Looks like this fails here, not in the middle. Watch what happens. See it go? And that right there, when it snapped, that was locating the max. So, certain materials are very malleable, and you get a lot of plastic range, where it hits that yield stress, and it starts to stretch more and more and more. This was not malleable. It broke at one instant. It didn't stretch at all. Take a look. It continued according to Hooke's law, and then it just snapped. It didn't ever enter that range where it started to get really stretched and then snap. So this material is not, or does not have the same properties as a material like metal, for example. Let's try and find one more. We'll look at plastic actually, and then we'll look at compression of concrete. That's a good one. So, what do you expect obviously for plastic? You expect it to stretch like plastic. That's the whole concept.
Stretchatron.
That was so delayed, Nora. So look, notice here, this from here to here was originally probably like this. All this range is already getting stretched here in the middle. Look, you've hit the yield stress a while ago, and now it's taking even less stress to continue to stretch it more. It's reducing actually. There it goes. See it? Fracture point, separated. Last one, concrete, let's look at it. What are we going to look at concrete in for a test? Compression. Concrete's not made for tension. Interesting. This is very interesting. Take a look. It's not being loaded axially. Yeah. It's being loaded on the side. I'm not sure why. This must be like a cylindrical specimen of concrete that's close to the top and bottom. Let's see if they do it axially next. See the fracture? Look, the fracture starts on one end. Shh, guys. The fracture starts on one end. This happens with wood a lot, and it propagates through the material. So it's only made it to the middle at this point. It's going to continue spreading up here. And then we're going to see the whole thing fracture down them. It's all right up here. See it? Interesting. Okay, this one's so stretching that reaches out and then falls down. Alright. Last thing for today. We're going to talk about a couple terms first. Okay, it's going to be the end of materials. What I plan to do for the next, we have a couple classes left still, is talk about structures, There's a pretty cool video on bridges that I want you to see. So we'll watch that one day. And then I'll probably give you like a short quiz / like half test like I've done in the past on materials and on structures, those two things. Okay, so this is toward the end of materials now. So in the boom lever competition, what you guys did is the exact thing in the first term. Strength to weight ratio. That was exactly what you measured. How much it could hold divided by the actual weight of the material. So materials have strength to weight ratios. You take the ultimate strength, you divide it by the actual weight of the material, you get the strength to weight ratio. Thermal expansion. What is thermal expansion? Why is it important? Focus now, please. Why is thermal expansion important?
It's talking about how much a material is cooled. So like,
Based on what?
based on the properties.
Thermal expansion.
Based on heat.
Heat. Okay? Heat flow or heat removal from something causes it to either stretch or compress. And we've alluded to that. You guys asked the question, or somebody talked about wood swelling in the summer. That's why your doors get stuck in the summertime. The humidity causes the door to swell up. Thermal conductivity. These windows are not good at insulating against thermal conductivity. A lot of heat is lost because they're not really good like double pane windows. Double pane windows usually have argon gas between them. Air or argon. Usually argon has a lower thermal conductivity value. It acts as like an insulation or a barrier. Heat does not travel through air very easily. It travels through metal easily, through glass easily. So thermal conductivity is the material property. Heat capacity. Heat capacity. Guys, stay with me. Heat capacity is the C value, MC delta T. The amount of energy needed in joules to raise 1 kilogram of that substance by 1 degree Celsius. It's pretty much the exact value you would use for the material when calculating how much heat is needed to change its temperature. You use this to measure calories in food. Okay, caloric intake, or it's measured by heating up the food until it really burns away. Viscosity. Viscosity is a fluid's desire to flow or not flow. The more viscous, the more it becomes like maple syrup or honey. Okay, that's viscous. Molasses, remember the molasses massacre we talked about? That was high viscosity. It does not move well. When you take your arm in the pool or in the summertime, at the beach, in the ocean, take your arm and do this underwater. The faster you push your arm, the more force is pushed back. The viscosity or the viscous force is proportional to the velocity of the object moving through the fluid. So if you move your arm faster underwater, there's more force against your arm. That's viscosity. Bulk modulus of compressibility has to do with an E value, but not for tension. Okay, not Young's modulus of tension or elasticity, but compressibility.